Hello everyone. In this video, we are going to start talking about solutions to the omitted variable problem by going over control variables and categorical variables. Going forward, I will assume that you've watched the previous video and you understand what the omitted variable problem is and why it arises. In that video, we discussed how having variables in the error term that are correlated with our explanatory variable, x for example, causes bias in our estimate of that variable's effect on the dependent variable. So the ideal solution to this problem would be to identify all the variables that are in the error term that are also correlated with x and get them out of there. Pull them out of the error term and put them into the regression, and keep doing that until there's nothing left in the error term, no other variables that have an effect on the dependent variable that are correlated with x. While this is the ideal solution, realistically, it probably won't happen. You're always going to have unobservable variables that are inside the error term. That's unavoidable. Hopefully we're able to find most of them that are correlated with x. But bear in mind that when we talk about addressing the omitted variable problem, a lot of times the best we can do is mitigate the problem, not necessarily completely eradicate it. As I mentioned, the most basic strategy for dealing with the omitted variable problem is to make the variables no longer omitted, to put them into the regression itself. And this is the strategy of control variables. Control variables are variables in the regression solely because they are correlated with the explanatory variable that we're interested in, and of course the dependent variable. The whole idea of control variables is to deal with the omitted variables by taking them out of the error term into the determining function. Now, we don't actually have to care about the controls themselves. They might not be interesting to us at all or have anything to do with our end goal, but they have to be there in order to establish causality for the variables that we do care about. In the example from the previous video, our company was interested in choosing a price. They didn't actually care about what people's income was, and of course they don't have any impact on income, they can't change that, but we had to have it in the regression as a control. Like I said before, the ideal situation would be to control for everything that's causing a problem, but the problem with that is that a lot of times variables are not available. The data might not exist, or they might just not be measurable. One benefit of having controls in a regression is that they sometimes enable us to do a data sanity check. Control variables are often common variables that have well-known effects, or at least well-known effects predicted in theory. So if we see an estimate for the effect of our control variables that doesn't make any sense, that might be a red flag to us that something is still going wrong in our regression. For example, suppose we're estimating a model of how much consumers spend. We run the regression and we put taxes and income in there. If we see that taxes have a positive impact on sales, that wouldn't make any sense. Taxes reduce sales. So that would be an example of a red flag that we would see in our estimates. That's not to say that you should always be suspicious of surprising results. Those can still happen, but it can also be a sign that there's still some endogeneity out there that we need to deal with. Or it could also mean that we have a non-random sample. Either situation means that there will be bias. When we are choosing control variables for a regression, remember that they are there because they are correlated with both y, the dependent variable, and x, the explanatory variable. If you add in a control and it is not statistically significant, then you might think about dropping it from the regression. However, it is very important to point out that this is not always a good idea. You always need to be careful about removing variables from the regression. Even if they're not statistically significant to a high degree, they might still be providing an important role in reducing endogeneity. So if you pull a variable out of the regression and all of a sudden your coefficient estimates greatly change, then it could be that by removing it, you are actually adding in more bias to the regression. You might also have a family of variables that are all related to each other that individually they might not look significant, but altogether they are performing an important role in endogeneity control. We aren't going to get into joint significance here, but what it means is individually they're not significant, but as a group they are. Remember also, there is no hard cutoff for significance. I mentioned in the last video that I do not support hard and fast rules when it comes to choosing variables. You might have heard in the past that if you have a regression with a variable that is not statistically significant with 95% confidence, you throw it out no matter what. This is not a good idea. If you start doing that without thinking about it, then you might end up with bias by accident. You don't want that to happen. Let's look at an example. We're going to pull up the dataset wages and run some regressions. We are first going to estimate a Mincer equation regressing wage on education. And then we are going to add the variable experience, years of work experience, to the regression and see what happens to our estimate for the effective education. Now, before we go and do that, I want you to pause the video and go through the steps we talked about in the last video. Ask yourself, what do I think the correlation between experience and education is, and what do I think the correlation between experience and wages is? You can then use those two signs to think about the sign of the bias, and we'll see if what we get lines up with what you thought. Let's run the first regression. For the Y range, I'm going to select wage, and for the X range, I will select education. Make sure labels is checked. The results show an estimate of 60 for the coefficient on education. This means that every year of education completed results in a $60 increase in the wage. If these numbers seem a little small to you, this is monthly wages in 1980, so keep that in mind. We've run this regression without experience in the model. That means that experience could be an omitted variable. Clearly, we would think that experience is correlated with wage. People with more work experience generally have higher wages, positive correlation. But how is education correlated with experience? Do people with more education have more or less experience? Well, if you think about that, if you take 4 years to get a college degree, that is 4 years of work experience that you would not have compared to somebody who started working immediately after high school. Therefore, there is a negative correlation between years of education and years of experience. Since we have a positive relationship between experience and wage and a negative relationship between education and experience, a positive times a negative is a negative, so we have a negative bias. That means that leaving experience out will cause us to underestimate the effect of education. Education looks less effective for improving wage because it's getting tangled up in the fact that the higher educated people have less experience, on average. So let's add experience into the regression and see what happens. I'm now going to change our X range to education and experience. We notice a few things here. First, experience has a positive estimate, meaning that more experience means higher wages, exactly what we said. Notice also that the coefficient estimate for education is $76 now, compared to $60 from before. Remember that I conjectured that there was a negative bias here, that we were underestimating the effect of education because of leaving experience out. So when we added experience into the regression, we were removing that negative bias, so our estimate went up. We've established that finding and using control variables is important to removing endogeneity and bias from our regressions. So far, we have dealt strictly with numerical variables, things like wages, prices, output, and years of education in the example we just did. However, many useful controls are not numerical. They're categorical data. You might think about the state of residence. The place where you live is not a number. Or we could think about marital status, married or unmarried, sex, male or female, race. None of these things are numbers. They are categories. So how do we incorporate these into a regression? We can't just put a piece of data that is not a number into a regression. So we're going to have to do a little bit of extra work. The solution to this is to turn our categorical data into dummy variables. Dummy variables are also called indicator variables because they indicate categories. I'll usually just refer to them as dummies. The main thing we need to know about dummies is that they have values of either 0 or 1. For any observation in the sample, the dummy has a value of 1 if the observation fits the category we're interested in, and a 0 if it doesn't fit the category. It's helpful to think about this as on or off. You're in the category or you're not in the category. For example, whether or not a person is employed is not a number, that's a category. So we can create a dummy variable, employed, that is 1 for anybody who is currently working and a 0 for people who are not. We need to talk about one common mistake that comes up when using dummy variables. When we are making dummy variables, we need to select a base group. The base group is the category within the data that all the others are compared to. We do not create a dummy for the base group. We create dummies for all of the other groups. Mathematically, it does not matter which group you select as the base group. What does matter is that you select one. Going back to our employment status example, a person's employment status, if they're in the labor force, will either be employed or unemployed. If we choose unemployed as the base group, we create a dummy for employed, 0 or 1. Or we could choose employed as the base group and create a dummy for unemployed, 1 or 0 for unemployed or not unemployed. So far I've only talked about categories that have two different groups, but we can make dummies for categories with lots of groups. For example, states. Suppose we have some data from all 50 states and we want to create dummy variables for the states. We're going to select one state as the base group, so we'll have 49 dummies, one for each remaining state. The regression will not work if we have full dummy coverage for all 50. We need to have one left out as the base group. Let's take a look at how this works in practice. I have a new data set called SD Categoricals. This is wage data from 2017 for South Dakota residents, where I've included several categorical variables that we can play around with. We're going to keep it simple first and create dummy variables for male and female. In Excel, we will use the if formula. I'll show you in a minute how that works. And then we're going to run two regressions. We're going to regress wage on age and a dummy variable for female. And then we're going to regress wage on age and a dummy variable for male and see how these two regressions look. In the dataset, you can see that we have a variable sex right here that is either male or female. Since there's only two categories here, we only need one dummy. I'll start by making a dummy for female. I'm going to use the Excel formula, if, and then this cell right here equals female, in quotes, then it'll be a 1, and otherwise it'll be a 0. You can see for our first observation, it's male, so we get a 0 there. I'm going to run this formula all the way down, and you can see for our second observation, female, so we have 1 here. I can do the same thing, creating a male variable, which is if our cell equals male, then 1, otherwise 0. I'll run that formula all the way down too, and you can see that everywhere where female is 0, male is 1, and vice versa. Remember that to properly run the regression, we're going to need to make our variables a continuous block. So I'm going to cut and paste age right over here so that we get them all together. The first thing I'll do is run a regression with wage as the dependent variable. And for the explanatory variables, I'm going to have female and age. Before we take a look at this, I'm going to run the other regression. But now, for the explanatory variables, I'm going to pick age and male instead of female, and run that. Let's copy and paste this regression so that we can compare these two. I mentioned earlier that mathematically, it doesn't actually matter which one you pick as the base group. Notice that our estimate for the age coefficient is exactly the same across the two. Notice also that the female coefficient on the regression on the left is negative 10,605, and The male coefficient on the right is positive 10,605. They're opposites of each other. What this tells us is that, on average, women make about $10,000 less per year than men. We can either have men as the base group on the left-hand regression, and then for female, that lowers that down, or on the right, we start with women as the base, and then for male, it will increase from that base. Either way, our results are the same. Let's think about this a little bit more. I'm going to use the first regression we ran with male as the base group and a dummy variable for female. I've written out the equation here. What we can do is look at how our equation will differ for female or male. For males, the variable female will have a 0 value, so this whole part of the regression drops out, and we just have wage equals 27,000 plus 320 times age. For female observations, that female variable will be 1, so with female as 1, that part stays in, and what we get is wage equals 16,607 plus 320 times age. If we used the other regression with female as the base group and male as the dummy variable, we would get the exact same results. Looking at this graphically, what we have are, instead of one regression line, we now have two. One for female and one for male, with a difference of 10,605, which is the coefficient estimate for our dummy. Both of them have age in the equation with the same slope, but they have different starting points. Let's continue on with one more application using this dataset. We've just established that there is a difference in wages between men and women. This is called the wage gap. Suppose we're interested in making a causal estimate of the wage gap. This is a big open question. To get an accurate estimate of this, we need to use some controls. So we want to think about which variables could be correlated with wage that are also correlated with whether you're male or female. Some possible examples would be marital status, education level, number of children in the house, hours worked. We could think of all kinds of different things here. We will start out with a simple regression of wage on female, just to get a baseline of what is the wage gap. This is simply the difference in the average wage between men and women. Not saying it is causal yet, but that's going to be our starting point. And then we're going to start to add some variables to the model and think about what happens and why. First regression we're going to run will have wage as the dependent variable and female as our explanatory variable. This result tells us that on average, female has a wage $10,776 lower than male. Let's first compare this with the regression that we ran before, where we had female and age. Adding in age, you can see that there is almost no difference in the coefficient estimate for female. So is age serving as a useful control here? Clearly, age is correlated with wage, but it's not really correlated with female. Women and men in the labor force are, on average, about the same age. So age wasn't really an omitted variable. It might be important to wage, but it's not removing any bias. Let's add another variable into our equation. That's going to be college. College is a dummy variable that I created earlier that indicates whether or not a person has graduated with a college degree. This also includes people who have gone on to get graduate degrees. To get a continuous block of variables, I'm going to cut and paste this over here and run a new regression. The X range is now going to be college, female, and age. What we notice here is, of course, college has a very large positive impact on wage, but compared to the last regression we ran, the estimate for the effective female is substantially bigger than it was before. It went from about negative 10,000 to over negative 12,000. So what it looks like now is the wage gap is actually bigger than we thought before. We can think about the sign of the bias that we just removed. College is positively correlated with wage, But college is also positively correlated with female. Women are more likely to finish college than men. So what we have there is two positive relationships that lead to a positive bias. When we added college to the regression, we removed positive bias, which meant that our estimate goes down. Now we had a negative estimate, so it becomes even more negative than it did before. We're not done yet though. Let's add one more variable. We are now going to add the variable typical hours. This is a variable showing how many hours does each person work in a typical week. I'm going to move that one over into our block of variables as well and run this regression. Changing the X range to now include all 4 variables. What we notice now is that our estimate for the effective female has changed drastically. It's now changed to about negative 8,000, a much smaller effect than we saw from the last one. Why would this be? We can see that typical hours is strongly positively correlated with wage. People who work more earn more money. But typical hours might also be negatively correlated with female. If women on average work fewer hours than men, we would have a negative correlation. Negative times a positive is a negative bias. So when we pull that bias out, our estimate goes up. It went up from negative 12,000 to negative 8,000. So by adding college and typical hours, we removed one negative bias and one positive bias, moving in opposite directions. We've only removed 2 sources of potential bias. There's probably thousands more of them out there, but this is a good start. Whether the true wage gap is bigger or smaller than 8,000, I don't know. Before we wrap up, let's look at one last variable, the marital status variable. The marital status variable has 5 possible values: married, single, which means never married, divorced, widowed, and separated. When we have 5 categories, that means we select one of them as the base group and we have dummies for the rest. Like I said before, it does not matter which one we pick, we just have to pick one. I'm going to arbitrarily pick single as the base group, so I'm going to have a dummy variable for married. We'll have a dummy variable for divorced, separated, and widowed. I'll use the if formula to make these variables. Now that I've made these 4 for the first row, I can copy these formulas all the way down, and we can see that these are working well. Our first observation is married, so they have a 1 in married, 0 in all the rest of them. Second one is single, so there's 0 in all of them. They're in the base group. This person is divorced, so they get a 1 here and 0 everywhere else, and so on. We're now ready to use these in the regression. Again, we need to make sure we've got a continuous block of variables, so I'm just going to move our male variable over here. We'll run a new regression with the X range encompassing all of our variables, going from typical hours all the way over to widowed. We now have our 4 marital status dummy variables here. These coefficient estimates here tell us that controlling for typical hours, college, female, and age, married people have, on average, an income $13,000 higher than never married people. Remember that we're always comparing to the base group. So divorced people have an income $7,743 on average, higher than never married people, and so on. The other thing we notice here is that our estimate of the wage gap has increased. So you can see that every time we add controls, that estimate is going to move around a little bit as we continue to pull bias out of the estimate. Like I said before, our work is certainly not done estimating that, but we have a good start.